Hi, I'm João Freire, and I'd like to present an empirical review of automated analysis tools on 47,587 Ethereum smart contracts. This is joint work with Thomas Durieux, Rui Abreu and Pedro Cruz from InescID and IST, University of Lisbon in Portugal. Blockchain has received a lot of attention for its promise to change the world. It has been used to secure digital art, to implement games, to track container ships, and it was even proposed as a solution to political issues. Many people believe that blockchain will disrupt many industries. One of the most popular blockchain platforms is Ethereum. Key to its popularity is the fact that it enables developers to write so-called smart contracts. These are programs that are executed across a decentralized network of nodes. The main language used to write Ethereum smart contracts is Solidity, a high-level object-oriented programming language. Smart contracts are at the core of Ethereum's value. However, it is far from trivial to write secure contracts. There have been attacks where millions of dollars worth of cryptocurrency were stolen due to security issues with smart contracts. And despite these high-profile attacks, serious vulnerabilities continue to appear. This has led to substantial effort from the research community to develop automated analysis tools, capable of detecting vulnerabilities in smart contracts before they are deployed. However, it is not at all easy to compare and reproduce this research. Even though several of the tools are publicly available, the datasets used to evaluate those tools are not. If one wants to compare a new tool with existing work, the current approach is to contact the authors of existing tools and hope that they give access to their datasets. And so, the first goal of our work was to create open datasets of vulnerable smart contracts that can be used to evaluate analysis tools and enable reproducible research. The second goal was to use these open datasets to obtain an overview of the current status of automated analysis tools for Ethereum smart contracts. In particular, we were interested in understanding what is the effectiveness of current analysis tools in detecting vulnerabilities in Solidity smart contracts. How many vulnerabilities are present in the Ethereum blockchain? And how long do the tools require to analyze the smart contracts? For our first goal, we created two new datasets of Solidity smart contracts. The first is called SB Curated, and it is organized in the 10 DASP categories. It contains 69 contracts with a total of 115 tagged vulnerabilities. Contracts are annotated by tagging lines with the corresponding category of vulnerability as shown in the image. The second dataset is called SB Wild and contains all Ethereum contracts with at least one transaction and with Solidity source code available in Etherscan. We processed more than 2 million contract addresses, we obtained more than 900,000 Solidity contracts, and then we removed duplicates. We ended up with 47,518 contracts with more than 9 million lines of code in total. So, for our second goal, we use these datasets to evaluate existing analysis tools. We started by considering 35 tools which were filtered according to 4 inclusion criteria. First, tools must be publicly available and support a command line interface. Second, they must support Solidity source code as input. Third, tools should only require the source code with no need for code annotations. And finally, tools must identify problems. This means that tools that only create artifacts, such as control flow graphs, are excluded. At the end of this process, we ended up with the 9 tools shown in the slide. To facilitate the execution of the analysis tools, we created SmartBugs, an executional framework that supports a plugin system based on Docker images, parallel execution of tools to speed up execution time, and an output mechanism that normalizes the way the tools are showing the results. We then use SmartBugs to execute the 9 selected tools on the datasets SP curated and SP wild. The results are as follows. When considering the smaller dataset, the results show that the 9 tools are only able to detect 42% of all the vulnerabilities. Moreover, they underperform in 3 categories: access control, denial of service, and front-running. Mithril outperforms the other tools by the number of detected vulnerabilities. We also investigated the combination of different tools, and we observed that the combination of Mithril and Slither detects 37% of all vulnerabilities, which seems to be the best trade-off between accuracy and execution costs. Regarding the second research question, we used the larger SP-wild dataset. In this case, the 9 tools identify vulnerabilities in 93% of the contracts, which suggests a high number of false positives. Oyente alone detects vulnerabilities in 73% of the contracts, mostly of the category arithmetic. Since we observed the potentially large number of false positives, we analyzed to what extent the tools agree in vulnerabilities they flag. The hypothesis is that if a vulnerability is identified exclusively by a single tool, the probability of it being a false positive increases. The blue bars in the figure show that the large majority of the vulnerabilities have been detected by one tool only. The categories arithmetic and reentrancy are where consensus was higher. Finally, regarding the final research question, we observed that on average, the tools take 4 minutes and 31 seconds to analyze one single contract. Slither is the fastest tool with an impressive average of 5 seconds per contract, and Manticore is the slowest tool, taking on average 24 minutes to analyze a contract. In summary, we have created 2 new datasets and an executional framework called SmartBugs that enable reproducible research in automated analysis of smart contracts. We use them for a large empirical review, and we found that there are many opportunities for improvement. We also found that the combination of certain tools might give better results. As next steps, we intend to continue extending our curated dataset, add new tools to SmartBugs, and use some of our findings to improve existing tools. All our datasets and code are publicly available. If you'd like to collaborate with us, please get in touch. Thanks for listening.